please welcome to the stage Principal SA Security AWS, Peter O'Donnell.
Hi. Really excited to have everybody here today. Working with customers for my 9 years here at Amazon Web Services, I know very well that many of you, perhaps all of you, are very interested in protecting your data. And cryptography is at the basis of that for most of our customers, providing cryptography not only at rest, but in transit, but also to identify and assure software connections to servers. My name is Peter O'Donnell. I'm a Principal Solutions Architect. I've been here for 9 years working with some of our largest and most challenging customers. What I know is that when I'm in the room with you, I'm the cryptography expert. But the truth is, as a solutions architect, I get to say we a lot. We invented the Nitro system. We have designed S3 to be durable. But of course, that was never my work. So it is my great privilege and pleasure to bring to the stage 3 cryptographers that have worked together for decades on cutting-edge cryptographic research that is finally now becoming a reality. And we're excited to bring this innovation to you and talk to you a little bit about their research, what can be done with it, what is being done with it, and what someday will be done with it. So let me please introduce Hugo Krawczyk, Tal Rabin, and Shai Halevi. Hugo is a cryptographer, best known for co-creating the HMAC algorithm. Shai Halevi has been a cryptographer working on advanced cryptographic techniques, including homomorphic encryption. And Tal Rabin is best known for her work with multi-party computation and threshold cryptography. All of them have received commendations and awards over the years and are members of all the relevant bodies in the world. These are 3 of our most premier cryptographers, and they've come to Amazon Web Services as of last summer. So let's get into it. Thank you all for being here.
Thank you for having us.
All right. So let's start at a high level. What brought you to Amazon Web Services?
So the 3 of us have been together for a long time, for over 20 years. We started our career together at IBM Research, where we mostly did theoretical work with some applications to more things that are being run in the internet. Hugo has a lot of work on these things. And from IBM Research, we decided to go on a little adventure together. Our WhatsApp group, in fact, is called The Adventure. And that adventure was to start a foundation related to a cryptocurrency called Algorand. And there, we were there for 3 years. But at some point, we decided that we want to do something different, that we really want to take the advanced techniques which we've worked on and developed for over 30 years, and to take them and to move them into practice, that people will actually use them. And we thought a lot of what would be a great place in order to do it, what would be a company that also would have a lot of impact due to the size of the company, but also that it would be a company that would be willing and have the vision in order to apply these things. And we decided about AWS. AWS is very customer-oriented and focused, and that's the goal. And these techniques bring more security and more privacy for customers. So AWS seemed like a very great place to be. And luckily for us, AWS thought the same thing. So here we are.
That's right. And so let's talk a little bit more. We know that security is our top priority here at Amazon. And believe me, that is not a marketing slogan. That is how we operate. Hugo, can you tell me a little bit more about the vision for the future here? What are the outcomes you're looking for?
Yeah. Well, we are trying to bring state-of-the-art cryptographic techniques, those that have been invented in the last 30 years, and hopefully new ones that we and others will invent. And the idea is to use these techniques to raise the bar for security for our customers, both at the level of hardening the infrastructure, but also enabling new services that these new techniques enable and before were not possible. And examples of such techniques are what we call threshold cryptography, that we may expand on it a little bit later, secure multi-party computation, and what we call crypto computing, which is, you can think of it as computing on encrypted data. And these are ways, technology that enables new ways for people to interact with the cloud and maybe most importantly to collaborate with each other. So we bring this level of defense in depth, and also helping customers to reach their requirements and responsibilities. And traditional encryption, while being very good for protecting data in storage or in transit, is not good enough for these kind of applications. So we need new techniques. So the idea is to bring this stuff to our customers in AWS.
That's awesome. Shai, Hugo mentioned this idea of cryptographic computing and computing over cryptographic data. Tell us more about that.
So generally, cryptographic computing refers to the ability of processing data without ever seeing it in the clear. One example of that is homomorphic encryption, where data is encrypted and being processed in encrypted form without ever decrypting it, without even having the decryption key. Other forms of it are distributed computing, where each participant in that computation only sees bits that seems meaningless when you see them in their own, but among all of them, they still can process the data. This can be used, as Hugo was saying, both to do private outsourcing of customers' data to the cloud, where the cloud can process it without seeing the data in the clear, or private collaboration, where there are multiple customers, all want to pool their resources together, have the cloud do the processing for them, but they don't trust each other or the cloud seeing their data in the clear. Some examples that you can think of are private queries to ML models. The cloud may have a model, you may want to query that model. Well, you may not want the cloud to see what you're querying for, so you can do that processing in this way. Other examples would be still in the realm of ML, you want to do federated learning, where multiple parties there want to collaborate on establishing the model or on developing the model, but again, each with their own data. Again, these techniques are useful there.
And also, Tal, I know a lot of your work has been around threshold cryptography. What is threshold cryptography?
So threshold cryptography is one of these advanced techniques, and the goal of threshold cryptography is to eliminate single points of failures in relation to keys. So for example, if you have a signature scheme, you have a secret key which signs messages, and this key is very, very important. But if you store it on a single server, even if you secure that server, there could be a mistake that an operator does when they come to serve the server, and by mistake, they do a memory dump. Now your key is in the clear. And this is what we refer to when we say a single point of failure. So threshold cryptography techniques come to eliminate this vulnerability. And how do they do it? Let's say, just an example, that your signing key is the number 11. If you store it on the server, the number 11 is there. But since we said we wanted to eliminate this point of failure, we will take the number 11 and we'll split it randomly into two numbers, 7 and 4. 7 and 4 equal 11. But these are random numbers. And we'll put 7 on one server, and we'll put the 4 on another server. Now, you can see immediately that I've eliminated the single point of failure, because if there is a memory dump, say on the server that has the number 4, nothing has happened. This 4 has no connection to the number 11. Somebody who sees that value still does not know what the signing key is. But we've introduced a problem now. Now we have a 7 and we have a 4. How do we sign? the purpose of this scheme was to sign. So in fact, Threshold Crypto also offers the mechanism to sign from these distributed pieces. From the 7 and from the 4, each server acting on their own, maybe communicating somewhat, can generate the signature. Now, the interesting thing is that we've raised the bar on security, yet for an outsider, the signature looks exactly the same. They don't know what happened on the back end. So we really are offering something that improves the security for anybody who uses these systems, while preserving the external simplicity of the signature and not interrupting
So such
it.
a scheme, as you say, not only would reduce the single point of failure were there to be a compromise of one of these instances, but also there's an availability angle to this as well, right?
100%. So I gave a very simple example because I wanted to be able to speak about it here. But the schemes, in fact, are more sophisticated. You can we call this splitting of the key splitting it into shares. We can split these shares in a sophisticated manner. Maybe you want 2 out of 3 pieces to create the signature. You split it into 3 pieces, and any 2 can create the signature. You can set the parameters whichever way you want it, but I'm going with 2.
You could scale it to a large number of servers.
Whatever you want, whatever suits your system. But let's say we do 2 out of 3, it does increase availability also. Because even if one of the shares is lost, we can recover. But also, let's say we did 2 out of 5. Any 2 could sign in parallel. That also increases availability in that way as well. So it's a very versatile techniques, which can offer a lot of amazing features. And of course, it depends on the application of what you need.
So not just, say, disaster recovery, but disaster tolerance in some way.
100%.
That's awesome. So we know that this idea of crypto computing over a large body of data, but there's also some theoretical background to this. Is that right, Hugo? Like this idea of proof that you can actually know that the system is working correctly.
Yes, designing a cryptographic scheme, systems, protocols is not easy, or what I always say is it's not very hard, but it's much easier to design it wrong.
That's right.
So when do we know that what we design is secure? In cryptography, there are no simulations or tests that you can do for the security. So actually, it's only theoretical tools that we have, and we refer to them usually as proofs. We prove mathematically that the system is secure, usually in cryptography under some assumptions. And there are ways of doing proofs by hand, and as have been done for hundreds of years. But these days we also have automated proofs, having machines that help us reason about these systems. But a cryptographic system that has not been proven, in most cases, is an insecure system.
That's right. And so I was thinking about our long-term view. Amazon is a place for long-term thinking and long-term ownership. Tell us more about what you're working on right now to benefit our customers.
Should I start?
Sure.
Okay. So this mechanism of threshold security, threshold cryptography, we decided to look at various Amazon systems. And one of the first systems that we looked at is IAM, which is Identity Access Management. And we looked at the back end, which holds the keys used for authentication of all our customers. If you're our customers, you are using this system, and it's providing you assurances.
1 billion requests per second. I am every day doing trillions of authenticated requests.
So the question is, what could we do? Of course, Amazon has an eye on security, and the systems are secure. as they are, but we wanted to offer defense in depth, to try and find how we harden the system, because attackers are becoming more sophisticated, more things can happen, and we want to really have more than one layer of security. So we approached IAM, and in fact, they will be introducing this threshold cryptography into their system. They're going to start building it soon, and hopefully it'll be available. And of course, again, as I had said about threshold crypto, you as customers, you won't even know that we have done this on your behalf and that the system really is more secure. For you, everything is going to stay the same, the speed, the availability, and so on. But the system will, in fact, the security will have been hardened. So, and I want to say one more thing. We're new. We just came and we approached these people. But you could see sort of the philosophy in AWS, the enthusiasm with which this group received what we were saying, and the interest in doing it were really, in fact, for us, quite amazing that it was so accepted, and which was wonderful to see.
That's cool to hear. I mean, AWS IAM, obviously one of our oldest services today, operating at a bonkers scale. We've invested a lot in this service over time. Dr. Neha Rungta is giving a talk either later today or tomorrow about our innovations in proving the correctness of this system. And so I always want to emphasize to customers that, you know, even the old stuff, right? Obviously, we're creating new services every day, really a lot of innovation there, but the level of an innovation and investment in the old stuff, the things that will never change, is certainly one of our main focuses here at Amazon. So speaking about research, and you know, Hugo, I know we'd kind of talked about an application in the contemporary area. I know that advertisement is a critical area where multi-party computation comes to bear. Is that right?
Yes, yes. So first, this notion of secure multi-party computation is a type of solutions or protocols that allow a set of parties to compute in a collaborative way some function. And I'll give some examples. But in a way that everyone brings their own input, their own data, but the only thing that is learned is the output of the function. No one learns anything about the input except for what can be derived from the output of the function. And the idea is similar to think that if you have a trusted third party where everyone gives their inputs and that trusted third party computes the function and gives out the output, but now you don't have that trusted party, so you run this secure multi-party computation to achieve that form of functionality without the trusted party. So one example, also something that we have been working in the last year, is in the area of advertisement. So that in advertisement, people run campaigns, and then they have to measure the success of these campaigns. People have used for a long time third-party cookies, for example, for doing that at the level of web browser, but now it's being discontinued. So here also, you can, and the advertisers need to check with different publishers, and publishers don't want to give all the information that they have, and the advertisers also don't want to give all their data. So you want to build a protocol that all the providers bring the data, and at the end, you learn some statistics. In particular, we were working on the problem of computing two statistical functions, reach and frequency. Reach is how many users have seen an ad, and the frequency is how many of them saw one time the ad, 2 times, 3 times, etc. And so we are building this together with the World Federation of Advertisers, which Amazon is part of it. So it's a project with different companies, but we built a multi-party computation for a solution for that problem that is being implemented, and yeah, so that's
That's
one
an
example.
interesting kind of angle there where we are going to talk about some future stuff that's genuinely spooky, but this is an example of a system that's been in place for a long time, but prevailing culture and even, you know, some pressure from stakeholders that it really needs to become more private. And that these techniques and this advanced research allows, say, an existing computing capability to raise the bar not only on security, but privacy. Shai, tell us about this idea of homomorphic encryption. What is homomorphic, and why does that kind of improve the overall privacy angle for things like storing sensitive data in a database?
Right. So homomorphic encryption is a somewhat new player in this secure computation game. Homomorphic encryption is a specific type of encryption that allows you to process data in an encrypted form, as I said before, without even having the decryption key. We speculated on the ability to do that for many years, but the first examples of encryption scheme that actually enable that are only 15 years old. So it's a relatively new technology, but it is coming into maturity these days. That we expect to have hardware acceleration for homomorphic encryption coming up within the next year or so. And so in AWS, we're trying to see where we can provide this technology to our customers to improve their security posture, to improve their privacy posture. Right now, the thing that we're doing internally is a relatively large-scale study of capability together with many industry partners. For example, the producers of these future accelerators or parties that have their own technology. And we're running studies to assess this technology and see what we can do with them. But again, it's a 15-year-old technology. Imagine trying to inventing the transistor 15 years ago and trying to come up with an idea of what it can do today. This is where we are right now. A few things that I believe are possible or will be possible soon, checking if two pictures are pictures of the same person when these pictures are encrypted. Or, as I said, doing private queries to certain machine learning models. Other things that you can do, private set intersection. Hugo talked about advertisers. The advertiser has a list. The publisher has a list. They want to see if anybody that visited this publisher site actually bought something on the advertiser. So each of them have a list. They want to know who is in both lists without revealing the list to each other. Private information retrieval. I have a key value store. I want to fetch a value by key without the store being told what the key was. These kinds of things, those are all possible with today's technology, and we're expecting a lot more things to be possible once these accelerators come. So we're currently in the process of trying to see what the technology can do and trying to take existing workloads that AWS currently has, for example, this picture matching service that we already have, and enable it on encrypted data so that the customer doesn't need to do much. All you need is to check the box saying, well, I want this data to remains encrypted end-to-end, and then the process will be run on encrypted data instead of the plain text data.
And this idea of a kind of a one-click adoption, of course, is really important to our customers. It's also really important for how we design services, right? Make it easier to do the right thing and harder to do the wrong thing. And I want to quickly come back to this idea of hardware acceleration. I'm old enough to remember putting SSL accelerator cards in my web servers 20 years ago, because most of this cryptography is predicated on hard problems that involve a lot of math. Can you say more about the role of a hardware accelerator in kind of enabling adoption without compromising performance or latency?
Right. I mean, the one problem with cryptographic computing, as with any other technology, it has a real cost. The hardware accelerator is crucial in making that cost tolerable so that customers can deploy these workloads with the added security, or maybe deploy new workloads that were impossible before because of security or privacy concerns without having to pay too much. It's crucial, And in addition to the cryptographic techniques that we bring, there is, of course, always the system engineering part of it, because once you have the accelerator, well, you need to route these workloads to these hosts that actually have the accelerator. So there are a lot of work in front of us, but we're getting there, and I'm sort of optimistic that we will have news for you within the next few years about that.
That's awesome. And Hugo, I know you've also been involved in some other cryptographic designs for other systems here at Amazon. Tell us about the Constellation.
Yeah, so we have been doing also work on the more traditional cryptography, bringing our knowledge and expertise to share with Amazon teams. So we've been involved with problems related to key agreement, key management, even password protocols, and also facilitating. One example is a design of key agreement for the Kuiper satellite project. Another thing is doing end-to-end security, where customers can back up their keys with AWS and still keep full ownership of these keys. And some other things, hopefully things that we will be able to talk more in future reinforced meetings. But yeah, I mean, we are doing the more advanced stuff, but not forgetting also the core basis of.
That's great. And of course, if you're a bunch of crypto nerds, as I assume you are, my people, obviously top of mind for a lot of folks these days is post-quantum cryptography. What does it mean that in a possible future that a sufficiently powerful quantum computer could come to existence? It means that some of the hard problems, this idea of the assumptions on which classical cryptography is predicated, maybe stop being hard problems. Tell us about where we are with PQ.
Okay. So first of all, as you said, all our cryptography is based on assumptions. We don't have, except for a one-time pad, we don't have a single system where there isn't an underlying assumption. And if this underlying assumption is broken, then the system is broken. For example, RSA, if we figure out how to factor numbers on a classical machine, RSA will be broken. So we still don't know how to factor on a classical machine, but we do know how to factor on a quantum computer. Now, just so you don't run out of here immediately and say, okay, it's broken, in order to break a 1024-bit RSA modulus, which is the product of the two primes, you need a minimum of 1024 good qubits. Most likely you need even 10 times more than that, and currently we are not there. I don't want to say when we will there because I don't know, but there are experts that range from, 10 years to never. So it could be anywhere in that range. And so what do we do, given that we know that once if a quantum computer exists, RSA will be broken, what do we do? So NIST was very proactive and saw this coming and put a competition in place for which people designed post-quantum encryption signature schemes, and there was a competition to decide which one is the best. What does it mean that it's post-quantum? It's based on different assumptions. It can't be based on factoring, of course. It has to be based on what we call some lattice assumptions. And this competition ran for quite a few years, and the candidates were chosen about a year ago, maybe a little bit more. And these are the protocols which NSA is requiring to use, and they have some timeline of when to deploy them. I want to say something. I said systems for signatures and for encryption. Signature and encryption are not the same as they relate to post-quantum. And why? If you encrypt something today with a something that are old assumptions, factoring or discrete log. Somebody might harvest your encryption from today, and later on, when the quantum computer is available, they would be able to decrypt your message. I don't know, I'm not important, my messages probably are not being harvested, though if they would be, people would be very interested at the end. But otherwise, but of course, big secrets that need to last for a long time might be harvested. Signatures, however, are not the same. Signatures, even if you harvest the signature now, it doesn't help you much that you'll be able to break it later. So there's a difference between encryption and signatures when it comes to when you should be deploying post-quantum.
It's interesting, and we, of course, have been investing in PQ for a very long time here at Amazon Web Services. Today, we have a hybrid scheme available on the TLS endpoints for KMS, Secrets Manager, and our file transfer products. This is important to understand the word hybrid, right? Because these are new algorithms, it would be terrible if these new algorithms introduced a classical vulnerability. So what we have today are hybrid schemes that use a mix of classical cryptography and post-quantum cryptography that you can experiment with today. Are they suitable for prod? Conceivably. Are they worth the latency trade-off? Maybe not today, because you likely don't have that store and harvest threat model, and if you do, you probably got a lot of defense in depth around that anyway. But you can search online, find our post-quantum website, and stay up to date with everything we're doing. It's a lot of really fascinating research. Hugo, can you tell us a little bit more about the store and harvest thing in the context of maybe the life cycle of the data? You could imagine that encrypting a quarterly earnings report, the durability of that cryptography has a timeline to it. So if you could break it in 6 months, but it's only secret for 3 months, well, maybe that's not a big deal, but you could imagine longer term data sets like health data that need to be safe forever.
Yes, so it's a very important point here about the post-quantum to understand that there is the encrypted data that is not in danger today. We are talking about that it may be in danger in X years, and as Tal said, X has different, people have different guesses for what X is and how many years until we have a very powerful quantum computer to actually break cryptography. So the data that is in danger is the data that is very sensitive for long term and such that the adversary is willing to harvest now, because in order to break it in 30 years, you will need a ciphertext that was created now. So only data of that high sensitivity will probably be targeted. And so, yes, so there is definitely a set of data that is important to protect already. What I always like to remind ourselves is that there are many other things that may be more risky for data if you don't manage the security well enough. For example, there are voices in the industry that want to eliminate, or at least have the option of eliminating forward security from TLS 1.3. Forward security is an element that provides very, very high level of security. And so the point is that you need to follow the best practices, even with traditional cryptography, not only with post-quantum.
Well, you mentioned TLS 1.3, which is interesting, and if I can embarrass Hugo for a second, your Sigma protocol is at the heart of key agreement in TLS 1.3. But TLS 1.3, a lot of customers, I get the question a lot, like, what do I need to do about PQ? What do I do? The simplest answer is adopt 1.3. When NIST finally finalizes these standards, they're not going to come to 1.2. So the simplest, shortest answer I can give customers about preparing for a PQ future is adopt 1.3. Let me make that clear. So we've talked a lot about our innovations and this incredible research from my colleagues here for the long term, but we need your help. Almost everything we've built here at Amazon Web Services, easily 9 and 10, we've built because customers asked for it. right? That's true from Elastic Transcoder a decade ago to things like SageMaker and Bedrock today. Customers asked us to solve some hard problems. Shai, tell our customers how they can help us help them.
Great. So the short answer is come tell us where it hurts. This is a very good time to have an impact on where do these techniques come in? What kind of problems you, the customers, or maybe your customers, encounter that makes it hurt to bring data to the cloud? Because most likely there are cryptographic techniques that allow you to mitigate these pain points and do it with a reasonable price. But as we said, we are new to AWS, and this entire idea of crypto computing is, well, maybe 10 years old. It's still getting in the process of making it to mainstream computing. So we really, really need your input on where these things have impact. In the examples of homomorphic encryption, what workloads do you really want to run on encrypted data? In the context of federated learning, where are the places where it really hurts to join the data in order to do the learning? All of these things, we really need your input on it. There's one thing that I want to say about something that's already exists. Tomorrow there is a session in the developer session, DAP 251, if I remembered correctly, where there is one example that already is integrated into Amazon Cleanroom. So if you want to go to that session, you'll hear about it. These are things that slowly start to appear in production, but now it really is crucial for us to understand what do customers want. When are these techniques just good to have? When are these techniques a necessity in order to be able to process things in the cloud? So please find us outside here in the halls, or if you're watching it online through your AWS representative, find us, give us feedbacks. This is the time for it to really make an impact on where these techniques are used.
That's right. And at Amazon, we use this very particular phrase, customer obsession. And Tal at the beginning kind of talked about like why they came here. It's because this is a place where we can build for our customers and on behalf of our customers.
So I want to add, in addition to the fully homomorphic, as Hugo described, there are also techniques that are multi-party that maybe you don't want just to be processing on the cloud, but you need to collaborate with other organizations. For example, maybe you're a health organization and you need to share data with another health organization and you're prohibited by HIPAA, but you still want to do some processing on the data. These things, the multi-party computation techniques also help with that. And of course, also the level of threshold cryptography, which we said hardens the security, gives you another layer of defense for your most sensitive keys. And we can help with those techniques as well.
That's awesome. At Amazon, we use this phrase, day one. We're still just getting started. So this feedback that we need from our customers to influence the research and the product development, it's foundational to what we do here. So with that, really want to thank everybody for their time today. We're going to wrap up here. Folks on the live stream, we're going to transition to some Q&A in the room. But I really want to thank our panelists here. Thank you so much. Let's do some Q&A.